Let me explain how a transistor works. After all that history talk, what is a transistor? So I am working on the consensus and the idea that we kind of know what a diode is. So a quick revision of a diode. I have a few things on a graph. It would be, but I can't ethically and legally do it, unfortunately. It would be a good thing, though. Hi, Blues. Welcome in. Hello, Silver. Welcome in, everyone. So you're just coming in the moment. Diode. We won't finish that sentence. A quick revision. A diode is a material, is a semiconductor, right? And we kind of studied this before. So a conductor is something that has valence electrons in a conduction band really, really close together. So when you put a voltage difference, the difference between the valence band and the conduction band is so small, the electrons are like, whee, let's go. In an insulator, the conduction band and the valence band of the electrons is so big, that gap, that energy gap is so big, it's called a band gap even, that the electrons, you give voltage, but they're not going to go into it. Maybe if you give enough, they'll eventually jump into it. But unless you give that amount of energy, they will not jump into the conduction band and electrons won't flow. Semiconductors are in between. They don't easily flow, but with a little bit extra energy, they will flow. And one of the things that we do use in electronics is a diode. It's an idea that we have something called an N-doped side of a diode and a P-doped. An N-doped means that we've put stuff into the silicon to make it ever so slightly, not ever so slightly, but we've made it electron prone, while the P-type, what we've made it is more prone to holes. So that came off weird. So what that means is that when we put these two different doped materials together, very, very quickly, something called the depletion region is developed over time. Now, when we have a depletion region that's developed, it means that there is an electric field, a huge potential buildup. A whole bunch of electrons and holes come across first. For every time an electron meets a holes, there's a pair annihilation occurring. So there's a net positive charge on one side and a net negative charge on the other. And so there's a huge barrier potential. This means that when we put it in a circuit in forward bias, as in we allow electron flow in the correct way, in this case it's this way, the current is actually that way, electron flow is this way, electrons can jump over that barrier if we meet the potential, something like 0.7 volts. This is a standard number. Hi Nerdvina, welcome in. Hello Uthrox. I wish I found you before Mark. No! Law is important. Law is important. So it's completely okay. How are you keeping, Nerdvino? No bias here. Well, there is bias. So forward bias is like, yay, once you reach 0.7 volts, the electrons can jump over the barrier. It's not even jump over. The barrier gets smaller and electrons have an easier time of getting through. In a reverse bias situation, if you're putting the current in the opposite direction, well, what happens? The depletion region actually quite literally gets bigger. There is no way electrons will flow. So a couple of electrons will move because you've, set up a positive voltage. Some electrons will move there. But after that, there's not anything left, right? Same idea with the holes going this way. They'll move in this direction, but after they've moved, this depletion region has grown to its maximum size and it won't allow electrons to go through. The electrons cannot jump over. They can't go from here, interact here, and get across this depletion region. So, what is a transistor? You have diode number 1, you have diode number 2, and we put them together. We have an N-doped material joined with a P-doped material. So this is just one diode. And another way of looking at it, it still only counts as one. No, it counts as 2 diodes. Don't listen to Gimli. This is another diode, a P and N diode. So one of them, you can look at it as being reverse bias, while the other one is in forward bias. So that is what a transistor is. So what I've done is I've drawn a schematic. Oh, the light is actually glaring on it. I turn it off. Will it have enough light in? A little bit dark, but hopefully it's just to reduce the glare so you can see this. this is a zoomed in diagram of a NPN transistor. And so the idea behind it is that we're making this work as a switch. And the idea behind it is electrons will not flow if we don't have this circuit. If I close this off right here, this will not happen. Why? So this is the part of the lesson that I hope I get into. Dark mode, exactly, Mullins. Happy to get some science in my coffee this morning. Cheers to coffee. Cheers to all the coffee people in the chat. Caffeine addicts unite. Where was I? Oh, I have notes. I have notes on this actually. I wrote a few scribbles just in case I get it. Now, just to point out the base. Just to point out a few parts of the diagram. This is zoomed in. This part here is called the emitter of the transistor. So remember, there's 3 rods coming out of a transistor. 3 holes. 3 rods. Holes are a different thing. There's the emitter at the bottom in this case. There's the base in the middle. And at the top is the collector. The middle will always be the base, by the way. So the only thing you always have to figure out is which the collector is and which the emitter is. But the one in the middle is going to be always the base. Okay, in the case of an NPN transistor, because you can have a PNP transistor, that's another one, which is the exact same thing, but in the opposite direction, by the way. But we'll study the NPN in more detail. All right. It's important to note that the emitter, the base here, is in forward bias. If you look over here, that's the exact same thing as electrons going like this. So from here to here, that's a normal forward bias diode. Yay, we can understand this. This is normal. We're happy with this analogy. Well, however, the base collector, this guy here from P to N, that's a reverse bias. So we have 2 situations. We just grabbed 2 diodes and we put them together and hoped for the best. Coffee rules. 3 leads. So remember, N is doped with electrons, P is doped with holes, N is doped with electrons. Remember that. Now, what did I write here? Okay. Yes. So, we've set up this circuit where we put a voltage source in our circuit. We have, let's say, something like 0.2 volts operating. Nothing happens. If this is operating at 0.2 volts, there's not enough voltage to get the electrons across the diode. Nothing happens. However, let's say we, magically, I'll say this number, 0.7 volts. We set this to 0.7 volts or higher. What ends up happening is we end up allowing electrons to flow from the N part, this part here. This is basically a zoomed in. This is a zoomed in schematic of this. We end up allowing electrons to flow into the P junction, and there are some holes inside the P junction. That's what a P doped region. The holes and the electrons interact. Remember what happens? That's the electron hole pairs. They form together and it creates electrons in the valence band. These are emitted into the base. Now remember, this guy is very, very thin. There's only so many holes and there's a huge rush of electrons when we get it into forward bias. So there's loads and loads of electrons coming in, but only a few holes for the electrons to replace. And so the valence electrons go here. It's a very, very small current, tiny, tiny current. However, we've opened the floodgates. Because we've opened the floodgates in this forward bias region here, loads of electrons have jumped in here that have not paired up with holes. So if you don't have a paired up electron in here, in this P region, they're free electrons. Insert some epic song about freedom of mankind. This means that the electrons, because there's a voltage potential up here, positive charge, electrons are negatively charged, it can just move freely into the N region and into the collector lead towards the positive voltage supply. Again, we're looking from this from an electron perspective, not current. So let's say I removed this part here, this part of the circuit. This doesn't exist. And I just put on a voltage of 5 volts. This is the only circuit we're looking at. The electrons will not flow. because there isn't enough energy to get them across this barrier. The only reason why electrons can flow to the collector in the first place is because the electrons can get into the p junction, into the p region, because of this annihilation hole pair that's happening here. Then the valence electrons go into the base, while the free electrons get to go to the collector. Did I confuse everyone? Is this very, very difficult? Am I making things more problematic than need be? I love it. It's very interesting how chat is so busy when we talk about like fluffy stuff, but then when I go really, really technical like this or ranty like this, chat is very, very quiet. It's either, you know what, I'm dropping ship, I'm not listening to this, or number two, you guys were very, very listening intently to it. I don't know which one. An electron is tiny, tiny, one of the tiniest particles that exist in the universe. In fact, if I'm not mistaken, we can't break it down in particle physics. An electron is a tiny particle. Listening intently. Just paying attention. Okay, I'm glad. Hopefully, I've explained that well. I know it's a bit ranty. There's amazing GIFs and YouTube videos to show the demonstration of this, but hopefully you understand. And this, and you might say, okay, how is this a switch? How does it work? Well, the idea behind it is that, about this. How does the switch work? Oh yes, this is the main circuit. This is the thing that we want because there's a lot of current in this. There's only a little current coming out of the base. Tiny, tiny, tiny current. You can even think about it as the bleeding current. It's the wasted current in our system, but we need it because this is our switch. The idea behind it is, think of this as if there's computer scientists here. This is your if statement. If current flows through here, let big current flow through here. If no current flow here, no current allowed to flow here. I don't know if that was a very good computer scientist analogy. Let me know. Does that make a little bit more sense how this system can be used as a switch? So the side current on the electron siphon. Oh, electron siphon. I didn't think about using it that term. That gets the, kind of. It's technically incorrect analogy from a fundamental physics perspective, but it kind of works. That is a side, because you got it going, you got the free electrons in here. You got the free electrons in here. There's just positive voltage, the electrons would want to go. A thing to remember is the difference between valence electrons and conduction electrons and what free electrons are. So we did do that with the diode thing. If you want to revise back, you're more than welcome to. I have a full YouTube series on this for 8 hours. I did, but also a couple of YouTube videos. If you Google, how does a diode work? I will even tell you exactly who's amazing at diodes. There's wonderful visual support on this. I think it's called circuit bread. Let me confirm or deny the rumors I'm spreading. It's circuit bread. They're amazing. They're not that big. I mean, 150k subscribers, I guess, but like they're not as massive as some of the other YouTubers I see. Circuit bread. Freaking amazing, because I appreciate the other big YouTubers, like something like engineering something that will explain how a transistor works, but it doesn't really explain. They give a fluffy analogy, but they don't show what happens at a fundamental level. And Circuit Bread really goes through it carefully, and they have amazing animations. They're very simple, but they're really good animations. So highly recommend Circuit Bread if you guys want to get better visual representation, because all I've done is drawn pictures, but imagine if I could show you what's actually happening with the holes as well, because there's hole flow happening too in this direction, this way. Is it allowing voltage to flow through NPN creates holes to allow electrons to flow through the NPN? Not the, it's I would say it's kind of the exact opposite, Purple. You're almost like the way I would say it, because the whole flow will only allow the electrons to flow from here to the base, like a 90-degree turn, okay? There is no whole stuff happening to get the electrons from here to here to here. It's the exact opposite. Because there are no holes left over in the p region, these electrons are free electrons, which makes them allowed or able to get to the positive voltage at the collector. Does that make sense? Exactly. There's no more. There's a little amount of holes. This is why the size is so different. When you allow current to flow from the emitter to the base, all the holes almost immediately. Very, very simple analogy. There's 1, 2, 3, 4, 5, 6. 6 electrons come in. There's only 2 holes available. The 2 electrons go into these 2 holes, and they create valence electrons. These valence electrons go through the base. This is the classical NP diode, the forward bias. This is the normal thing that happens. But because we allowed this flow into the P junction, there's 4 electrons left over that did not annihilate with a hole. They're just free electrons. And because this is where I use the analogy of opened the floodgates, these free electrons are allowed to float into the positive collector lead. I know, there's so many weird things I'm saying. There's no holes in the P region. I know. Not really, chocolate mints, because it's not electrons hitting the valence band. So if you remember your energy bands, again, I'm so sorry. This is based on diodes, and maybe I should have had some diode prepared. Remember the depleted region. The energy bands. So this was the valence. And these are the conduction band. The free electrons are already in the conduction band, and they don't need the energy to get over the barrier like the electron hole ones. I'm so sorry. Maybe I should have covered that a bit more. Is there a bit of increased resistance when the holes are all occupied? Is there a bit of increased resistance? No, because you got rid of the holes, the 2 holes there, the holes need to be replaced. And so there's a whole electron. There's a whole electric flow. So for this model to work, you have to think of holes and electrons as 2 separate things. And there's actually hole current and there's electron current. So this is the electron current going in this direction, while in this direction we have hole current. And it does get replaced because every time a new cycle has to continue. For every hole that is created, another hole gets replaced, then another electron goes in, then another hole gets created, then another electron comes in. It's a continuous cycle. I took a whole electronics class with all this info and have forgot. Same, Zaga. I did this like 11 years ago. I don't remember any of it. This is what I mean by keeping your brain active every day. Chat. Do a little thing to keep your brain active. Or pick up a hobby with some brain activity. But yes, this is something that I also didn't learn really well when I was a student. But, you know, studying as an adult is way more interesting. I say this all the time, when you're an adult, you're more honest with yourself about what you don't know or do know. When you're a student or when you're young, you're not very honest with yourself. Well, I wasn't anyway. Now that I'm more honest when I don't understand something, it's such an important step forward into learning anything, I guess. The minute you accept that you're wrong or I don't know shit is the biggest step forward you can make to truly start learning things. In my professional scientific opinion. It's a way, that's a way of thinking about it, Purple, yes. Or the other side, ignorance is bliss. That's the other part about it, yes. It could be pride. In my case, it was embarrassment. I was too embarrassed to admit that I didn't know things. I was too, yeah, that's why I didn't admit to knowing things. So, now that I've explained how a junction works, a quick thing to also add to this is two mathematical equations. This one is super important. What did I call it? I have my lecture notes. In case, because we have a few new people here, I lecture this. This is, I'm teaching this next semester, so I'm preparing lectures on this. And what I do is I prepare a couple of para slides and I test it on you. So if I said something wrong, correct me. If I didn't explain something the best way, let me know, because I'll improve for my own real students. Sorry to call them my real students. But I always forget what this is called. The equivalent hybrid parameter. No way am I ever learning that off. So, transistors have a number. You will know that when you look at a transistor, I think I have some around here. I need to look for them. They will have a number on them. And the number can sometimes be called a current gain number, or sometimes an equivalent hybrid parameter. That's what the HFE stand for. There's the same thing in a transistor, by the way. In a BJT, they're the same thing. It gets more complicated later, but for these guys, it's actually nice and simple. And all it is, supposed to be an equal sign there, is it's the current gain over the base current. What does that mean? It's this current over this current. Now, chat, let's think about it. After everything I just ranted there for the 10 minutes or so, 20 minutes maybe. Why is there... Okay, so you know why there's a little current here. We start off by getting a little current here to turn on the switch and make this work. Yay. Chat, why do we want it as little of a current as possible though? Why do we want this current to be big and this current to be tiny? The tinier, the better. One of the rare times a lady will say that to you. But the tinier this current is, the better. I only know that I know nothing, and then a rabbit hole until I know enough to move on. Rabbit holes are really nice. I really enjoy a good rabbit hole. Quite literally, in my case, because of my bunzo. Badumts. So we can ignore it. You're on the right idea. Less power consumed, less power wasted. So this is our switch. As soon as there's a current going, this works. And that's all we want. We want a current to work here, and that's it. It doesn't do anything in our power system, whatever system it is. This is just a yes or no. This is a yes or no statement. And when it's yes, we want as much current in our system to be going through here. So it'll never be 100% efficient, but we want as much current as possible to go through here. So the collector current over the base current, that value should be as close, as high as possible. Because this one number, we want it to be super, 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 super big. And this one, we want super, 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 super small. Big number divided by small number is equal to big number. Okay? This number is usually, in most transistors now, between 20 to 200. And remember we were reading the article that the first demonstration of the transistor in history was 18. That was the value. It was 18 for its current gain. Now transistors are easily over, I think it's hundreds even now that they can do, but usually anywhere between 20 to 200, depending on what you need. But this is why this current gain value is really, really important. And this is the number that will be shown to you when you read the data sheet for your transistor. So if you ever see a beta DC value, or if you see this HFE, which is the, I always forget it, sorry. Let me look at my laptop. Where do I have it? Equivalent hybrid parameter. That is what it is referring to. Exactly. We only need enough current to turn on the switch. That's all we needed to. We needed to overcome the voltage first, and that's all we really, really needed. Another number is this alpha parameter. Yeah, it's just called DC alpha parameter. DC stands for direct current, in case you're wondering what the D and the C stand for, direct current. Sorry, my eye is itchy. And this is equal to the current collector. It's the current coming out from the top over the emitter. So So the current going in and the current going out. What kind of number is that going to be, chat? Let's get our brains working. This number divided by this number. Anyone have any ideas? A real number. Good answer. Good answer. So it's a ratio number of the collector current over the emitter current. Let's get our brains working. Fundamental thermodynamics physics. Energy cannot be created or destroyed. We have current going in here. A little is splitting here. Majority is going up here. What can you say about this alpha number? Finish my iced coffee. Should be less than 1. Nice. Good job. So it should be less than 1. The number on top. Okay. Classic thermodynamics. Statistical physics. All the electrons going in here only have 2 paths to take. This one and this one. So the base plus the collector should equal to the emitter. Common sense, right? Okay, common sense is a bit rude of a statement. But can we agree on this? All the electrons coming up here have 2 paths to take, base and collector. So the sum of all the electrons in the collector, the sum of all the electrons in the base should equal to the emitter. Classical thermodynamics, statistical physics. Energy cannot be created or destroyed. We cannot create matter out of nowhere. The electrons have to go somewhere. That's where they all are. So when we put the current from the collector over the emitter, we will always get an answer less than 1. Because ever so slightly, some of the current is going to the base. In fact, the more closer to 1 it is, the better, generally speaking. Because that means it's very little current going this way. If it's really, really, really close to 1, like 0.99, it means very little current is going here, and most of it is going here, which is very, very good. But in terms of experience, the alpha number can exist between 0.95 and 0.99. Those are generally good values for alpha. Not all data sheets will have it, by the way. You might not always know. So just be aware of that you might not know this number. You could calculate it. If you do this demonstration. In fact, kind of a misleading thing. It's not really misleading, but in case you're worried, it's like, oh my God, so a transistor, you need 2 powerful sources. You can do this demonstration at home. Just make sure your resistors are good enough, as in maybe 500 ohms or whatnot, and you're only working with a couple of volts. But you can use the same voltage source. All you need to do is use a potential divider here. And how do you do a potential divider? Put a resistor in series. And you can make sure that your diode is experiencing a different voltage one side versus the other. Okay, now that I've ranted for the last 20 minutes or so, if not longer, did we learn anything today, chat? Was today an educational stream?